complex craft. At 121 feet long and weighing 80 tons, it was roughly the size of the American Skylab. The spacecraft consisted of two major components: the functional cargo block, which was repurposed from spare modules of the Mir space station, and it housed maneuvering rockets, solar panels, and power systems; and the purposeful module, which contained the planned laser weapon, fuel tanks, and generators. To launch it, the USSR relied on the Energia rocket, a new heavy-lift vehicle originally developed for the Buran space shuttle. Peleus's only flight happened on May 15, 1987, atop an Energia rocket. Initially, the launch appeared successful, with the rocket delivering its payload to orbit. However, a combination of rushed design choices and software errors led to disaster. The spacecraft's reorientation maneuver, intended to align its engines for orbital insertion, failed due to a faulty inertial guidance sensor. Peleus's failure marked the end of the USSR's space weapons program, and it symbolized a broader decline of Sovietism. Its cancellation after years of development, significant financial investment, and unrealized potential makes it one of the most remarkable examples of failed space infrastructure. The origins of the MOL can be traced back to the 1960s, when the U.S. Air Force and the National Reconnaissance Office sought to harness the strategic potential of manned surveillance from space. The concept revolved around a crewed space station that would orbit Earth at polar altitudes, capturing high-resolution imagery of strategic targets in the Soviet Union and other regions of interest. Each mission was to last about 30 days, with 2 astronauts conducting operations aboard a station launched using Titan III rockets. The astronauts would travel to and from the station in a modified Gemini B capsule. This program was officially approved in 1965, and its goals aligned with the broader objectives of military and intelligence dominance in space. But despite the lofty vision, the MOL program faced challenges from its inception. By 1969, it consumed $1.4 billion, with little to show for the investment beyond prototype hardware and one uncrewed test flight. Systems were not only cheaper, but they're also more practical for delivering high-resolution imagery. Additionally, the Bureau of the Budget under President Nixon's administration scrutinized the program's costs, which were deemed unsustainable. Even the United States Air Force arguments about the MOL potential advantages could not outweigh the economic and technological realities. Number 13. The X-33. The Lockheed Martin X-33 was a bold attempt to revolutionize space transportation in the 1990s. It was conceived as part of NASA's reusable launch vehicle program, aimed at creating a single stage-to-orbit vehicle that would significantly reduce the cost of access to space. The X-33 was intended as a suborbital technology demonstrator for the Venture Star, a next-generation reusable spaceplane designed to be far more efficient and cost-effective than the predecessor, like the Space Shuttle. The X-33 would test several key technologies, including a metallic thermal protection system, composite cryogenic fuel tanks, an aerospike engine, and advanced flight. Now, this plan called for a sleek spaceplane with a 70-foot wingspan that would be able to take off and land like a conventional plane, but with the ability of reaching low Earth orbit. However, the project ran into serious hurdles from the start. One of the most critical issues arose with the vehicle's component liquid hydrogen fuel tank. The idea was to use lightweight composite materials to reduce the mass of the tank and make the vehicle more efficient. That's a key factor in achieving its goals. In November 1999, the composite tank failed during testing, revealing issues with micro-cracking in the core. This setback proved to be a significant blow to the program, as the technology was simply not ready for such an ambitious application. By 2001, NASA had invested nearly $1 billion in the program, with Lockheed Martin contributing an additional $350 million. But it was clear that the X-33 could not deliver on its promises. While some later technologies developed through the X-33 program would contribute to further space exploration efforts, such as the development of composite cryogenic tanks, the Venture Star never flew, and the dream of a fully reusable, cost-efficient space plane remained just that, a dream. Number 12. Transhab. The idea behind Transhab was simple yet bold. Inflatable modules. They could be compact when uninflated, allowing for easier and more efficient launches. Once deployed to space, these modules would expand to a diameter of 27 feet, offering astronauts more living space than the 14-foot diameter of the Columbus ISS module. Transhab, as the name would suggest, was originally conceived as a transit habitat for human journeys to Mars. Well, the inflatable shell consisted of numerous layers of material, including Nextel insulation, foam padding, Kevlar for structural integrity, and Kevlar blended materials like Combitherm to hold air and prevent leaks. Internally, Transhab was designed with 4 levels: a pressurized tunnel area, a crew healthcare and exercise space, crew quarters, and of course a kitchen and a wardroom. These modules were intended to support the crew's daily activities and provide all the necessary equipment for long-term space missions. Each crew member would have their own quarters, along with personal space for work, rest, and recreation. But despite the promise, when alternative options like leasing inflatable habitat modules from private companies were available. Number 11. HOPE-X. The HOPE project, short for H-2 Orbiting Plane, began in the late 1980s as a partnership between the National Space Development Agency of Japan and the National Aerospace Laboratory of Japan. Japan was at the forefront of space advancements during this time, having already developed the N-1 and N-2 rockets and successfully launched its first satellites. With ambitions of contributing to international space efforts, Japan sought to design a reusable spaceplane that would also serve as a key component for the Space Shuttle program, and later the International Space Station. By the mid-1990s, Japan had a string of successes in space exploration, including the launch of the H-2 rocket and successful tests of various re-entry and heat-shielding tech. In 1994, the OREX re-entry vehicle tested critical systems for the upcoming spaceplane, and in 1996, the HyFlex project demonstrated the feasibility of carbon-carbon heat tons to the ISS, roughly the same amount as the Russian Progress spacecraft. As the deadline for HOPE-X approached, the project continued to encounter problems. The reorganization of Japan's space agency in the early 2000s, following the formation of the Japan Aerospace Exploration Agency, was prompted by Japan's broader economic stagnation, increasing national defense concerns. By the time of its cancellation, NASDA had spent about $305 million on the project since its inception, a modest sum considering the scale of the intended spaceplane and the multiple failed efforts to get it off the ground. Number 10. Project Daedalus. Launched by the British Interplanetary Society between 1973 and 78, Project Daedalus aimed to design an uncrewed interstellar probe that could travel to another star system within a human lifetime. The probe was to be propelled by a fusion rocket, an engine capable of achieving speeds far beyond anything achievable with current or even foreseeable chemical rockets. The target, refinement fusion. It's a method that would use electron beams to ignite fusion pellets, releasing massive amounts of energy to propel the spacecraft. The design proposed a 2-stage craft. The first stage would take the probe to 7.1% of light speed, while the second stage would accelerate it to 12% of light speed, a speed that, while impressive, still falls short of the 10% of light speed considered the magic number for interstellar travel. The spacecraft was planned to be built in Earth orbit and would have a staggering mass of 54,000 tons, with 50,000 tons dedicated to fuel. The mission design also included innovative ideas like autonomous sub-probes, and once the Daedalus spacecraft reached the star, it would launch these probes, which would travel at 12% the speed of light, passing close to nearby planets and relaying data back to the mothership for transmission back to Earth. The spacecraft would carry a beryllium shield to protect its equipment from the harsh conditions of space, and ahead of the ship, dust-collecting vehicles known as dust bugs would clear debris and smaller architecture to support that venture. The spacecraft's weight was also so great that many of the project's proposed technological elements, such as the sub-probes, were impractical without significant advances in propulsion or energy storage. As such, Project Daedalus joined the ranks of some of the most spectacular space dreams that were too ambitious to turn into reality. Number 9. The Almaz Military Space Station. The Almaz Military Space Station was a secretive Soviet project that aimed to push the boundaries of space warfare, focusing on reconnaissance and offensive capability. Born out of Cold War tensions, it represented a bold vision of what military power could be like in space. In the early 1960s, the USSR envisioned a space station that would not only gather intelligence but also serve as a platform for offensive space weaponry. This program was highly classified, with its existence only being acknowledged long after the Cold War ended. At its core, it was intended to be a reconnaissance outpost equipped. A major issue was the sheer technical complexity and the difficulty of executing such a project. The payloads and sensors were behind schedule, and with the rise of unmanned satellites, the Soviet military began to lose interest in human-crewed space missions. The project faced a further blow in 1970 when the USSR realized they could gain political capital by launching civilian space stations. This led to the creation of the Salyut program, which was based on components from the Almaz project. While three of the Salyut stations were essentially disguised versions of Almaz spy stations, the political and economic shift made it clear that the future of Soviet space exploration lay in civilian rather than military missions. And by the late 1970s, the Almaz program was effectively finished. Number 8. Mars Direct. One of the most controversial space exploration projects ever conceived is often remembered not for its accomplishments, but for its spectacular failure to move beyond the drawing board. Proposed by Robert Zurban in the early 1990s, the result was predictable: political resistance and complete withdrawal of funding within a year. But amid the political fallout, NASA's focus shifted away from crewed missions, opting instead for robotic exploration with the mantra of faster, better, cheaper. Zurban's analysis of the SEI found that the proposed mission strategies were unsustainable, often relying on overly complicated, expensive tech. The missions would have resource utilization by extracting carbon dioxide from Mars's thin atmosphere and combining it with hydrogen to produce methane and oxygen for return fuel. This was a simple and bold approach that would greatly reduce costs and complexity. Internal resistance within NASA, though, and competing missions like the space station and advanced propulsion studies led to the eventual rejection of the Mars Direct plan. Zurban didn't give up easily, though. In the early 1990s, he tried again to convince NASA officials of the merits of Mars Direct, but NASA's priorities were shifting. As the space agency adopted a faster, better, cheaper strategy, failed space infrastructure projects ultimately canceled due to an unsustainable budget and a series of challenges that proved too difficult to overcome. The idea for TPF started with the growing interest in exoplanets, planets that orbit stars outside our solar system. In the 1990s, the discovery of a few extrasolar planets fueled a wave of curiosity about the possibility of finding Earth-like planets. The idea of detecting these planets directly, rather than just through indirect methods, became an attractive goal. The question wasn't just, do other Earths exist, but also, could we find evidence of life beyond Earth? First, it was the Infrared Astronomical Interferometer. This architecture aimed to use multiple small telescopes placed in precise formation. By using a technique known as nulling interferometry, these telescopes would block out the starlight, allowing scientists to detect faint infrared emissions from distant planets. NASA's initial enthusiasm led to TPF's inclusion in the agency's budgetary plans. In 2000, explored Jupiter's moon Europa, but this wasn't enough to overcome the growing financial challenges. Number 6. The Sea Dragon rocket. The Sea Dragon rocket. This was a concept so grandiose that it could have revolutionized space travel had it ever been built. The idea for this massive, low-cost, sea-launched rocket emerged in the early 1960s, driven by aerospace engineer Robert Truax while he was working with Aerojet. Its size was a defining feature. Standing 490 feet tall and 75 feet in diameter, it would have been the largest rocket ever constructed, even compared to modern-day giants like the Saturn V or SpaceX's Starship. At the time, his concept was considered a solution to the high cost of space access. The Sea Dragon was envisioned as a big, dumb booster, using simple and inexpensive materials like 8mm steel sheeting for construction. Truax had already tested similar concepts with smaller vehicles like the CB and Seahorse, and this experience helped him refine the Sea LOX, designed to expand its engine bell during flight to improve performance. Truax's plan for the Sea Dragon were clear: a low-cost, highly efficient rocket that could be mass-produced. Yet, despite initial interest from NASA and some shipyards like Todd Shipyards, the project faced overwhelming technical and financial challenges. The sheer scale of the Sea Dragon, coupled with the shift in focus towards smaller, more modular rockets like the Saturn I and later the Space Shuttle, made the Sea Dragon's size and complexity an impractical solution for the time. Number 5. The Space Elevator. The space elevator is often hailed as one of the most audacious ideas in human engineering. It stands as an example of how grand visions can sometimes fall short of the practical demands of execution. A space elevator is a proposed transportation system where a cable extends from Earth's surface near the equator into space. The cable would stretch all the way to a counterweight in geostationary orbit, about 20 to help popularize the space elevator in the West, through a 1969 speech before Congress where he expanded on the feasibility of the concept. In the 1990s, engineers began experimenting with the idea. The first significant gathering of experts took place in '99 at NASA's Advanced Space Infrastructure Workshop, where the idea of a space elevator received serious consideration. Interest led to a series of competitions designed to foster the necessary technologies. Elevator 2010 competition, hosted by the Spaceward Foundation, focused on developing the climbers, cables, and power systems that would be needed. While there were a few notable advancements in developing the technology, such as the creation of prototype climbers and cable designs, the breakthrough material necessary to build the elevator cable was elusive. The issue of creating a material capable of withstanding the immense forces of gravity, centrifugal acceleration, and the environment of space remains unsolved. In the meantime, researchers were eyeing alternative solutions such as macro-scale graphene, which could potentially offer the infrastructure projects marked by groundbreaking innovations that just couldn't secure a future due to lack of sustained funding and an eventual shift in NASA's priorities. The idea behind the DCX was to demonstrate the potential for a fully reusable rocket. Now, the concept of a vertical takeoff and vertical landing had been explored in science fiction for years, but real-world attempts were either incomplete or never fully realized. Max Hunter, a key figure behind the DCX project, had been advocating for such a concept for over 30 years. The inspiration for the vehicle came from his former colleague Philip Bono, who had proposed similar ideas, including the one-stage orbital space truck, but none of these ideas advanced beyond the drawing board. In 1989, after years of unsuccessful attempts to gain traction in the industry, Hunter managed to secure funding for his VTVL rocket through a meeting with Vice President Dan Quayle. The Strategic Defense Initiative Organization, driven by the need for a reliable, quick turnaround rocket for military use, saw that the DCX's funding stopped. The concept of vertical landing rockets didn't. SpaceX and Blue Origin in the years that followed resurrected the idea, with both companies achieving their own successful vertical landings. Despite its untimely cancellation, the project demonstrated what could have been a revolution in space travel, a reusable rocket capable of fast turnarounds and low costs, had it received more support and resources. Number 3. The Dyson Sphere. The Dyson Sphere, as an idea, is probably one of the most ambitious space infrastructure projects to never happen. It's the vision of how a far future civilization might deal with its ever-growing energy needs, yet its practical execution remains utterly out of reach. While it is a grand concept on paper, its sheer scale and complexity make it more of a thought experiment than a feasible endeavor. The concept of a Dyson Sphere traces its roots back to 1937, when science fiction writer Olaf Stapledon it would eventually need to harness the power output of its star directly. Dyson's vision of the sphere wasn't a solid shell, as commonly depicted in science fiction, but a collection of independent structures orbiting the star, collectively known as a Dyson swarm. Now, while Dyson's paper sparked interest in the concept, he never proposed a way to actually build such a structure. It's clear now that executing this idea would be far beyond any current or near-future technology. The idea of constructing a solid shell around a star, as often depicted in fiction, is mechanically impossible. The structural integrity required to hold such a shell together would collapse under the immense forces involved. Even Dyson himself dismissed the idea of a solid shell, referring instead to a loose collection of objects in orbit. That's the Dyson swarm. Despite the inherent impracticalities, the Dyson Sphere became a staple in science fiction. Writers like Larry Niven and Frederick Pohl explored variations of the concept, often with more fantastical depictions. The most iconic of these is the reach back to the late 1940s, when physicist Stanislaw Ulam, working at Los Alamos, proposed the idea of nuclear pulse propulsion. Ulam's basic concept involved detonating nuclear bombs behind a spacecraft to create thrust. This idea was refined further by Ulam and fellow physicists like Freeman Dyson and Ted Taylor, who began developing it into a practical space travel solution in the mid-1950s. In 1958, the project received official backing from the U.S. government, with DARPA agreeing to fund the initial research at a rate of $1 million a year. The design was simple in concept, a series of nuclear bombs that would be detonated behind the spacecraft, each explosion sending a pusher plate surging forward, and then would be absorbed by the shock absorber system to prevent damage to the spacecraft. This propulsion method offered a combination of high thrust and high efficiency. That was a breakthrough compared to traditional chemical rockets. The test showed some promising results, with models reaching an altitude of about 100 meters using 6 chemical detonations in 1963 effectively killed Project Orion. With the ban on nuclear detonations in space, the project's primary propulsion method became illegal. The military applications also lost favor as the Air Force saw fewer immediate uses for the technology. By 1964, Project Orion was officially canceled, with the team pivoting to other, less controversial methods of space propulsion. In fact, if the project had succeeded, Orion could have made interplanetary travel possible within a human lifetime, drastically reducing travel times to distant planets. Number 1. The Freedom Space Station. Space Station Freedom, a bold idea proposed in the 1980s, aimed to create a permanently crewed space station in low Earth orbit. It was a NASA-led multinational project, originally intended to be a collaboration between the United States, Japan, Europe, and Canada. The station's goal was to serve multiple purposes, such as an orbiting repair shop for satellites, a base for spacecraft assembly, a platform for scientific experiments, and even a micro-boost the space station route, particularly under the assumption that the newly developed space shuttle would drastically reduce the cost of building and launching such a station. The Freedom Space Station's design evolved over time, with several concepts and redesigns brought forward. The initial design, called the Power Tower, envisioned a long central structure with modules at each end, designed for stability and ease of alignment with Earth. As the plans progressed, various configurations were explored to cut costs and make the station more feasible. By 1989, the project had grown considerably in complexity. The program's original $15 billion estimate quickly ballooned as the project continued to overrun costs. As the 90s progressed, political and financial realities led to the eventual collapse of Space Station Freedom in its original form. NASA faced mounting pressure from both Congress and the American public. This constant reshaping, combined with growing financial constraints, made it clear that the project could not survive in its intended form. In that same year, President Bill Clinton's administration